Machine learning has moved past the era of data scarcity. The new bottleneck is the precision engineering required to produce high-quality synthetic datasets. Many professionals still view AI data generation as a task of writing clever prompts to generate infinite text. A naive approach, like a single Python loop pushing prompts to an API, yields a jumble of unformatted, error-ridden output that downstream databases cannot parse. Modern AI engineering replaces this unpredictability with a scalable, deterministic data factory, utilizing orchestration, validation, and storage. We architect this factory through three layers: the generation engines, the fine-tuning optimization layers, and rigid quality gates. AI engineering focuses on the architecture that constrains a generative model's output, transforming an unpredictable API call into a reliable data source. The foundation of any pipeline is the raw generative engine. For text and tabular data, pipelines utilize transformer architectures. For computer vision and synthetic images, engineers rely on latent diffusion models using the UNet reverse denoising process. One common pattern is teacher-student distillation, where a massive GPT-class model generates a stream of explanations and preferences. By capturing the logic of an expensive model in formats like RAG triples or instruction pairs, we can transfer high-level reasoning to a smaller, open-source student model. However, full model fine-tuning of these base engines is often too computationally expensive for a continuous data pipeline. Parameter-efficient fine-tuning, specifically low-rank adaptation or LoRA, provides a more efficient architectural solution. LoRA injects trainable adapter layers into specific modules, such as UNet attention projections, bypassing the need to retrain the billions of base model weights. This method makes the continuous, programmatic adaptation of models to specific domain data economically viable. Post-generation, the primary challenge is the erratic nature of the model's output. Unstructured text or hallucinated variables will immediately break downstream training scripts. Every production pipeline requires a schema validator. Tools like Pydantic allow engineers to force an LLM to output strictly typed data, mapping every generation to explicit key-value pairs. Any data failing the typing or schema link validation is immediately dropped from the pipeline. Engineers use two primary patterns to feed these structured schemas. Prompt-based generation uses a large LLM to generate entirely new examples based purely on instructional logic. Seed-based augmentation uses real domain data in the prompt to constrain the model's variance and enforce consistency. Rigid schema validation is the only way to transform unpredictable model output into functional engineering data. The viability of a synthetic data pipeline is defined by its survival rate, the percentage of records that withstand rigorous automated vetting. The data factory utilizes a sequence of automated quality gates to refine raw output. Gate 1 uses deterministic filters to scrub toxicity and uses tools like SD metrics to ensure PII reduction and privacy preservation. Gate 2 applies an embedding similarity filter to prevent repetition and mode collapse in the dataset. By calculating the distance to closest record in latent space, the pipeline removes records that lack sufficient statistical diversity. The sparse remaining cubes enter Gate 3. A large scanner reads each cube, stamping them with numerical confidence scores. This judge scores the data against metrics like instruction following and groundedness, rejecting any low-confidence outputs. Only a small fraction of the original volume of blue cubes successfully exits the third gate, now glowing white to indicate final approval. Raw synthetic data is detrimental to downstream models unless it is culled by these mathematical and programmatic gates. Scaling a validated pipeline requires moving from a local prototype to a massive, concurrent production system. Orchestrators like Airflow or Dagster wrap the pipeline logic to manage complex dependencies and retries. Engineers use batching and async Python within the orchestrator to manage thousands of concurrent generation jobs without memory faults. To maintain speed, the system uses VLLM for high-throughput serving of generation models during asynchronous bursts. Managing these pipelines requires the same level of experiment tracking as traditional software codebases. Datasets are versioned using tools like DVC or LakeFS, preventing regressions when generation parameters are modified. MLflow logs the outputs of the quality gates, providing an auditable record of the pipeline's historical performance. The system logs specific telemetry, including validity rates, diversity scores, and infrastructure latency. Orchestration and rigorous lineage distinguish a fragile experiment from a robust, auditable software system. The completed architecture involves LoRa-optimized generation, pydantic schema structure, latent space culling, and async orchestration. This factory's output is used for one purpose: training a specialized target model. The primary benchmark of success is downstream model lift. This metric measures the performance improvement of the target model when tested against real-world, human-validated data. As foundational models become commodities, the primary competitive advantage for any team is the programmatic architecture of their synthetic data pipeline.